So planet data. So just at the end of the lesson, students should be able to interpret data to compare the Earth with other planets and moons in the solar system with respect to properties including mass, gravity, size and composition. So it's really about being able to look at this information and draw different conclusions from that. So let's have a look. So this is our solar system here. So we can see that in this solar system as well is kind of roughly to scale. So it gives you kind of a sense of the size of each of the planets and the sun in comparison to each other. So just looking at it, so if we have a look here, we can see that the sun is absolutely massive in comparison to the size of the Earth. So this is the size of the Earth here. And we can see then, the inner planets, these planets here, or the terrestrial planets as they're known, are quite small in diameter in comparison to these Jovian planets, okay, or the gaseous planets that are further out in the in our solar system. So they're quite big. So this is our solar system. So I'll just give you a few minutes just to have a look at this and maybe to study it, and just make some observations. You can see just looking at it, the size of, for example, Mercury, even the size of Mercury in comparison to the size of Earth, and look at the size of Jupiter in comparison to the size of the Earth. So imagine like this, all of our existence happens on this tiny blue dot, and look at the size of that in comparison to Jupiter. And then if you take Jupiter and try and compare it to the size of the sun, it's only a fraction. It's a tiny fraction of the size. We can see as well, it also shows the moons that the planets have. So we can see that Earth has one moon, and we can see that Mars it's shown two of the moons here. If we go out into Jupiter, then we can see all of these guys here. Saturn has all of these guys, Uranus has these, and Neptune has these as well. Also as well, it shows the asteroid belts. So we have an asteroid belt here. And then we also have the Kepler belt as well, this guy out here, where you get a lot of comets. And inside here you can see Pluto, for example. And Pluto is not a planet because it doesn't have its own orbit, and it's not the right size, and it's also kind of contained within this Kepler belt, so it's in amongst lots of other asteroids and meteors and things like that. So the first property we look at is mass. So first of all, we need to try and understand what exactly mass is. So mass is a measure of matter, okay, or inertia. So basically matter is, if we remember, it's made up of different types of atoms. So, and those atoms are made up of protons, neutrons, and electrons. So basically, mass, so matter, for example, atoms have mass, okay, and that mass, it comes from the protons and the neutrons that are present in the nucleus of the atom. So that's kind of like where mass comes from. So mass depends on the number and kind of atoms that an object has. The mass of an object is the mass of an object regardless of where the object is. So for example, we have weight and mass. Mass is just like how many, it relates to the number of atoms, the type of atoms and the number of atoms that make up the object. Whereas weight is its mass, okay, so it's the number of atoms and the type of atoms, but then also as well the force of gravity, which we look at later. And the unit that we use to measure mass, so we can use kgs or grams, okay, or kilograms. Now, so in this case, we're going to look at kg. Now, what we want to think about then is the mass of the planets. So this is, like, these are mind-bogglingly big numbers when we start to talk about the mass of a whole planet, for example, and if we look at it in kgs. So if we have a look here, so we have the main planets that are in our solar system, and beside it we have the mass in kgs. So if we have a look at this, the mass in kgs, it's in scientific notation. So we can see that it's written 3.3010 multiplied by 10 to the power of 23. So to get an idea of how big that number is, so it's written in scientific notation. So if we just simplify this and we just write it as, so let's say 3.3 3.3 multiplied by 10 to the power of 23. So 10 to the power of 23 is 10 multiplied by 10 multiplied by 10, 23 times. Or another way to kind of think about it is it's 3.3 and then with 23 zeros after it. So if I had something like this, so 3.3, and then if we put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that's the size of this number here, kgs. So that's the mass of the planet Mercury. So we can see that this is an absolutely huge number. And when we have big numbers like that, we use this thing that's called scientific notation. So you can just take this number and then we can write it as 3.3 multiplied by 10 to the power 23. That's 10 to the power 23. So you're moving the decimal 23 places to the right. So it gives you an idea of like how big these numbers are. So if we have a look at this, and this is another way then we can take all of this data and display it and compare them to each other. So the masses of the Earth and other planets. So what this is doing is it's comparing the mass of all the other planets to the mass of Earth. So if the mass of Earth is just 1, then everything else is wrote in terms of that. So if we have a look at Jupiter, for example, so Jupiter here, so Jupiter is huge in comparison to the size of Earth, so it has way more matter in it. So Jupiter is 317 times, so 318 times the mass of Earth. So we can see that if we look at these objects and excluding the Sun, we can see that Jupiter has the most mass, okay, has the most matter. Then would be Saturn, and then we're probably looking at Neptune and then Uranus. Now, in comparison to all of them, the Sun is absolutely massive then as well, so it dwarfs all of these planets. So the first kind of property then that you can look at is this idea of mass, and obviously when we're talking about the mass of a planet, we're talking about it's a measure of how many atoms make up that planet, and the numbers, as we've seen, are absolutely huge. So they are like these are huge bodies of matter that are in space. The next then kind of property that we can look at, and it's related and links in with mass, is this idea of gravity. So gravity is basically a force, so it is, and the force of gravity acts between objects. So basically, in order for there to be gravity, there has to be mass. So when you have two masses, what happens is there's this force of gravity. It's like a force of attraction between the objects. The bigger the mass, the bigger the force of gravity. So we can see here that you have like these are bigger objects that have more mass. So therefore, like, and it's signified by the arrows in the middle here, the force of gravity between those objects are much bigger. Now, it's mass and then it's also distance then as well from each other. So the more further apart the bodies of matter are from each other, the less the force of gravity. The closer they're together, the bigger the force of gravity. So gravity is a force essentially. The more matter you have, or the more mass that's present, the bigger the force of gravity. So if we take the Earth, for example, in comparison to us, the Earth is a huge object. It has loads of matter. And what that does is we feel that force as gravity, in that we're stuck to the Earth. So we are. Now, if we, for example, get in a rocket and fly outside the atmosphere and we go up into the International Space Station, which hovers outside of our atmosphere up here, and what happens is the further we get away from the mass, the less there's a force of gravity. So if you look at any pictures that you see with astronauts on the International Space Station, they're actually moving around and they're floating around. Why are they floating around? Because the force of gravity is not as strong. Now, in our solar system, the sun has the biggest mass, and therefore it has the biggest force of gravity on all of these other smaller bodies or smaller objects of mass. And what that force of gravity does is it essentially keeps all of these planets orbiting around the sun. So you can think about this force. So there doesn't need to be physical contact between the objects. The force of gravity operates across the vacuum of space. So if we have a look at this little demonstration here, it kind of gives us an idea of the force of gravity. So on either side we have these two objects. So we have object 1, which has this mass here, 100 kgs, and then we have object 2, which has this mass here, which is 400 kgs. And we can adjust and change these as well. And what we can see up here, this arrow, this indicates like how strong the force of gravity is. So if I take these two objects and I increase the distance between them, okay, so I increase the distance between these two objects like this, we can see that the force of gravity is actually it reduces the force of gravity. We can see that in the arrow. Now, what are some of the things I can do to start increasing the force of gravity? Well, I can put in more mass. So if I increase the mass, like so, okay, that slightly increases the force of gravity that we can see up here. If I increase the mass of this object then as well, okay, we can see that the more we increase the mass, that actually increases the force of gravity between the two objects. So you can link in the force of gravity with mass. The bigger the mass, the bigger the force of gravity. The other thing then that we can do is, so let's say if we reduce the masses down, so when we reduce the mass, for example, we can see that the arrows start to shrink, the force of gravity starts to decrease. Now, what's the other things that we can do to increase the force of gravity? So let's say if we keep the masses roughly the same, let's say, so 200 kg and 200 kg, how can I increase this force of gravity between these two objects? What I can do is I can move them closer to each other. So as we move the objects and we decrease the distance between the objects, what starts to happen is you'll see that the force of gravity, as they become closer, the force of gravity starts to kick in. And that happens, so if you imagine this object here is the Earth. Okay, imagine, so this is the Earth here. And imagine this object, the other object over here, if we make it much smaller. So imagine this is like a rocket, for example. So what's going to happen? So when it's out in space out here, it's outside the Earth's atmosphere. What's going to happen is it's not going to really have the force of gravity from the Earth, for example, if this represents the Earth, is not going to be very strong in it. But the minute this object starts to come close to the Earth, what will start to happen is the Earth's gravity field will start to suck it in, and what will happen is the force of gravity will start to increase. And what that force of gravity will do is it'll essentially pull the object towards the surface of the Earth. So that's the force of gravity, and the force of gravity is linked to the mass, and it's also linked to the distance between the objects then as well. So we can measure gravity in newtons per kg, or just G. Okay, so this is the letter that we use. And if we have a look at these objects, we can start to compare. So this is the force of gravity, for example, on the objects. So if we take the Earth, for example, the force of gravity on Earth is 9.8. Let's say if we were then to go to Mars, which is here, and we can see, if you look at Mars, it's smaller in size and diameter and mass than the Earth. So what we can see, we would expect then to see that the force of gravity would be a bit less on Mars, and we can see that here. So the force of gravity on Earth, it's 9.8, on Mars it's 3.7. And if you're on Mars, you would experience that as slight weightlessness. Okay, so you wouldn't need as much effort, for example, to move around on Mars. If we take then as well, if we were to go to the moon, so for example, we have the moon here, we can see that the moon is much smaller in mass than the Earth and Mars. And we can see that the force of gravity on the moon, for example, is 1.7. So it's much smaller than on either of the planets. And again, for example, if you were to weigh yourself and get your weight on the moon, you would weigh less than your weight on Earth. So remember, weight is a measure of, weight is a force, so it's related to your mass, which doesn't change unless you lose mass. it's the force of gravity and your mass. So for example, if your mass stays the same, your weight, for example, on Earth would be higher than your weight on the Moon. Why? Because the force of gravity acting on your mass is much stronger on the Earth, much stronger than it is on the Moon. Now, if we jump up here to the Sun, for example, the force of gravity is huge on the Sun, and we can see that. We can see in comparison to all of the other planets, it's actually huge. And then if we were to look, for example, at Jupiter or Saturn, so these guys here, we can see that the force of gravity on Jupiter and the force of gravity on Saturn is much stronger than on Earth. Why is that? Because the masses are much bigger. If we look at the size of these in comparison to the Earth, they're much bigger. So again, gravity is it's a property that we can look at and we can measure. The next kind of property then that you can look at in relation to the planets in our solar system and the moons is their size. So we can, just looking at this, and it's a really good diagram, we can see the huge difference in size between these celestial objects on the sun. So we can see that, in diameter, the sun is obviously going to be one of the biggest, and then we can see next to that would probably be Jupiter, and then next to that would be Saturn. So again, we have here the diameter, and we measure the diameter in kilometers. So if we take the diameter of Earth, okay, so that's the diameter of Earth, it's 12,756 kilometers. And if we take the diameter of Mercury, we can see that it's smaller than the diameter of Earth. And here we have size relative to this, in percentage relative to the size of the Earth. We can see, so if the Earth is 100%, then in comparison to size, we can see that these planets in here, some of them are roughly around the same size, others are quite smaller. And then if we go out here to these Jovian planets, we can see that they're actually way bigger than the Earth. So again, size is a property or a data point that we can measure in relation to the size of planets. And then the last kind of property we want to look at is this, what's called composition. So composition is really like what the planets are actually made up of. Now, if we take the periodic table, so this periodic table identifies all of the building blocks of matter in the universe. Okay, so this is essentially what makes up everything in the universe. You can think about them like the building blocks. So everything in the Earth, essentially, everything in the universe started off as hydrogen, and then what happens is hydrogen, when you get enough of it in a particular region in space, if the mass of hydrogen increases, that increases gravity, and then what happens is you get hydrogen then starts to be forced together by the force of gravity, and that causes a nuclear explosion, and that's the start of a star. And then what happens is, if you compress two hydrogen atoms together, it makes helium, and then if you compress helium and a hydrogen atom together, you get lithium. Okay, and then if you keep compressing these together, you start to get all of these other atoms here on the periodic table. But when we're talking about the composition of the planets, we're interested in looking at these planets. So we know that the planets here on the inside, these inner planets, or terrestrial planets, they're generally like rocky and metallic types of planets. And why are they like that? Because the closer you get to the sun, the hotter it is, and these are the only kind of planets that are going to survive those conditions of heat from the sun. Once we move out here away from the sun, it starts to be much cooler, so these are kind of like gas planets, gaseous planets. They're made up of gas. So let's have a look at like what's the actual composition of each of the planets. So if we start off first of all with Mercury, so Mercury is this guy here, it's the closest to the sun, and it's made of, so it has rock and silica. So silica is like materials that have silicon, or they're like some of the compounds that contain silicon in it, and silicon is this atom here. And then what it has then in its core, it has an iron and a nickel core. So we can see that iron is this Fe element on the periodic table, and nickel is this element here as well. So you can think about it's like a silica crust, and then it has this, so it's like a rock or silica crust, and then it has this iron and nickel core in the center. Then as we move out to Venus. So this is Venus here as well. So again, same type of core. You have iron and nickel. That's its core. and then it has a silica based like a crust. Okay, so it's rock, so it's essentially rocky and metal. Then we move out further and we have iron and nickel again in the core of the Earth, and then you have like silica rock then as well. Okay, so very similar to these planets as well. And then we move further out, so we have Mars. So again, it's rock and silica and iron and nickel core. So again, these are the terrestrial planets. Then as we move out further, then if we come out to Jupiter, for example, so Jupiter essentially is it's essentially like water and rock. So it has a water and rock core. Then it has metallic hydrogen. Okay, so it's like hydrogen, a metallic version of it. And then what you have then is you have molecular hydrogen gas. So you have hydrogen again out here, gas, and it's changing to liquid at its base as well. So essentially this is all hydrogen, and what's happening is this gaseous hydrogen starts to turn into liquid hydrogen here inside the core. Then we move out further and we have Saturn. So again, Saturn has a rock. It has a rock and metallic and watery inner part, and then again it has this hydrogen gas on the outer part then as well. And then as we move further and further out, we have Uranus, which is a rock base. It has water and hydrogen gas molecules, so it's mainly made up of rock and hydrogen and water. And then we come out to Neptune, and has again a water and rock core, and then it has like pretty much ice and water on it. And then we have Pluto, which is in here as well. So again, it has rock core, and it's mainly like H2O, which is in frozen water, if you like, around on the surface of it as well. So that's when we talk about the composition, that's what we mean. That's what we're talking about in relation to the composition. So we can see that the main elements that make up these planets are these guys here, and they can be found on the periodic table. Okay, so that is that. So students should be able to interpret data to compare the Earth with other planets and moons in the solar system with respect to properties including mass, gravity, size, and composition. Okay, so thank you for listening.